There is an asteroid in our solar system that, by every measurement we have, should not be able to exist. It is called 33 Polyhymnia. It has been sitting in our catalogs since 1854, and it appears to be denser than any natural material the universe is allowed to make. More than 3 times denser than the densest element on Earth. By volume, it is roughly 1,000 times larger than the interstellar object 3I/Atlas. Big enough to hide a factory. Big enough to hide a machine. Scientists call the number impossible and move on. But what if impossible is exactly the disguise something would want? Stay with me, because the reason they can't explain this rock may be the most unsettling part of all. If a rock that shouldn't exist is your kind of mystery, subscribe to the Quiet Archivist. Tell me below, should we actually fly out and check Polyhymnia or leave it alone? Now, let's get into it. On August 6th, 1945, at 8:15 in the morning, the city of Hiroshima vanished into a light brighter than the sun. In that single instant, a species that had spent 200,000 years scratching at the surface of its planet did something no living thing on Earth had ever done before. We unlocked the power inside the atom. We crossed a threshold, and the flash of that crossing did not stay on Earth. It raced outward in every direction at the speed of light, a sphere of radiation and gamma rays and hard physics expanding into the dark, carrying a single unmistakable message to anyone in the galaxy who happened to be listening. The locals just learned to split the atom. 2 years later, the skies over the United States filled with something nobody could explain. On June 24, 1947, a pilot named Kenneth Arnold was flying near Mount Rainier in Washington state when he saw 9 objects moving in formation, shining, skipping across the air the way a flat stone skips across water. He described them as saucers, and a phrase was born that would haunt the next 80 years: flying saucers. Days later, in the first week of July, the town of Roswell, New Mexico, made headlines across the country when the United States Army announced, and then very quickly unannounced, that it had recovered a crashed flying disc. And then the floodgates opened. Sightings poured in from across the country, then across the world. Something, all at once, seemed to have become intensely interested in us. It is tempting to draw the obvious line between those two events. We light the first nuclear fires in 1945, and within 2 years, the visitors arrive to see what the noisy new neighbors have done. Cause and effect. The bomb was the dinner bell. But the moment you actually do the arithmetic, that tidy story falls apart, and it falls apart in a way that is far stranger than the story itself. Here is the problem. The nearest star system to our own is Proxima Centauri, part of the Alpha Centauri group, and it sits about 4.2 light-years away. A light-year is the distance light travels in a year, and light is the fastest thing the universe allows. So when the flash from Hiroshima went out, the very earliest that any watcher parked around Proxima Centauri could have even detected it, could have seen the faint evidence that an atomic detonation had occurred on Earth, is late 1949. The signal simply cannot arrive sooner. That is not a technological limit. That is a law. Now give that watcher every advantage. Say they detected our bomb the instant the light reached them in 1949, and say they launched a ship that very day. Give them a starship that can travel at 99% of the speed of light, which is, as far as we understand physics, the practical ceiling for anything that has mass, anything built of atoms. Even then, crossing those 4.2 light-years takes them more than 4 years. From their point of view, they would not arrive at Earth until 1953 or 1954 at the earliest. I want to make sure that speed limit really lands, because everything downstream depends on it, and most people have never had it explained plainly. The 99% of light speed I just gave the aliens is not a number I picked to be stingy. It is a gift. and a generous one. As far as we understand the universe, nothing that has mass can ever actually reach the speed of light. The closer you push it, the more energy it takes, and the cost climbs toward infinity as you approach that final edge. To shove a starship to 99% of light speed would already take a quantity of energy that beggars imagination, more than our entire civilization produces in a year, poured into a single vehicle. And even with all of that, you still do not beat the clock on a 4 light-year trip. You still take more than 4 years, because that is simply what 4 light years means. The distance is baked into the word. So, when I say the visitors would have arrived in 1953 or 54 at the earliest, I am being as kind to the alien starship idea as the laws of physics will allow me to be. And it still does not work, but the saucers showed up in 1947. They were early, not by a few weeks, not by a margin you could explain away. They were early by 6 years or more. The visitors arrived before the light of our threshold could possibly have reached even the closest star and summoned them back. And that single broken timeline is the crack in the floor that this entire investigation falls through. Because if nothing traveling at or below the speed of light could have gotten here in time, then either the rules of physics we have staked everything on are wrong, or we have been thinking about this the wrong way from the very beginning. What if the visitors in 1947 were never responding to Hiroshima at all, because they did not have to travel here to see it? What if they were already here, and the bomb only woke them up? Hold that question, because to take it seriously, you first have to meet the kind of thing that could have been waiting. To understand what could have been sitting in our solar system, quietly, for a very long time, you have to start with a question that has tormented scientists for more than 70 years. It is one of the simplest questions you can ask, and nobody has a good answer for it. The physicist Enrico Fermi is supposed to have blurted it out over lunch one day, and it has carried his name ever since. The question is this: where is everybody? Think about the numbers. Our galaxy is enormous, with something like a few hundred billion stars. It is also old, far older than the Earth, with billions of years of head start during which other worlds could have formed, cooled, grown life, and produced creatures clever enough to build machines. Even if only a tiny fraction of those stars grew civilizations, the galaxy should be crowded. It should be loud. And yet, when we point our instruments at the sky and listen, we hear nothing. No signals, no beacons, no traffic. The universe, as far as our ears can tell, is silent. That silence is the Fermi paradox, and it is genuinely unsettling, because the math says the sky should be full, and our eyes say it is empty. Now, here's where the silence gets sharper, almost cruel, and here is where you meet the real subject of this story. In the 1940s, a mathematician named John von Neumann, one of the most brilliant minds of the 20th century, worked out the underlying logic of a machine that could build copies of itself. He called it a universal constructor. On paper, it was a set of rules, a proof that a machine could, in principle, take in raw material and assemble a perfect duplicate of itself, which could then do the same, and so on, without end. It sounds abstract until you point it at the stars, and then it becomes one of the most powerful and frightening ideas anyone has ever had. Picture a single spacecraft, not crude, not enormous, just a clever automated probe. It is built to do 3 things, and only 3 things. It explores. It harvests raw material from whatever it finds, the way we are already planning to mine water and metal from the moon and from asteroids in the very near future, a technique engineers call in situ resource utilization. And crucially, it builds copies of itself. So this one probe drifts into a new star system, finds an asteroid loaded with metal and ice, and gets to work. It mines. It refines. Using onboard fabrication, robotic arms, 3-dimensional printers, powered by sunlight or by something nuclear, and guided by software smart enough to run the whole operation alone, it manufactures solar panels and processors and engines. And then it assembles not one, but dozens of identical copies of itself. Daughter probes. Those daughters launch toward other asteroids, other stars, and each one repeats the entire process. That is exponential growth, and exponential growth is a kind of quiet violence. 1 becomes 10, 10 become 100. A single probe, replicating patiently across the gulfs between stars, could fill an entire star system with copies in a few centuries. And it could saturate the entire galaxy, every promising star, in a few 100,000 to a few million years. That sounds like a long time, but against the age of the galaxy, which runs to billions of years, it is the blink of an eye. No warp drive required. No faster-than-light magic. No crude generation ships carrying fragile passengers across the dark. Just patient, relentless, self-replicating machines, multiplying in the silence. People have proposed all sorts of escape routes from the Fermi paradox, and it is worth knowing them so you can see why the probe idea is so quietly devastating. Maybe civilizations always destroy themselves before they spread. A grim idea sometimes called the Great Filter, the notion that something reliably kills intelligent species before they can fill the galaxy. Maybe life itself is just vanishingly rare, and we really are close to alone. Maybe everyone is out there, but deliberately staying quiet, listening, and hiding rather than broadcasting. Each of those is a real, serious answer that real serious scientists argue about. But the self-replicating probe slips past most of them. It does not need its makers to survive. The civilization that launched it could have risen, flourished, and died a billion years ago, and its machines would still be out here, multiplying, indifferent, carrying out their orders long after the hands that built them turned to dust. You do not need a galaxy full of living aliens. You need exactly one dead one that built a single clever machine before the end. And in a galaxy of hundreds of billions of stars across billions of years, asking that not even one civilization ever did, that begins to feel like a stretch. And that is exactly why the silence is so loud. Because if these machines are possible, and nothing in known physics says they are not, then the first civilization to build even one should have flooded the galaxy with them ages ago, including this corner of it, including here. So either nobody ever built one in a galaxy of hundreds of billions of stars, which strains belief, or they are already here, and we simply have not recognized them. And recognizing them would be the hard part. Because if you were designing a probe to survive for eons and go unnoticed, you would make one specific choice above all others. You would tell it to hide. You would build its outer shell from local material, so it carries the same color, the same reflectivity, the same chemical fingerprint as the ordinary rocks around it. You would tell it to go dark, to power down for thousands or millions of years, broadcasting nothing, because its job was never conversation. Its job is to watch, to replicate, and to wait. And you would give it one instruction for when to wake up. Stir only when something interesting happens. A burst of radio noise, the signature of industry, or the unmistakable flash of a species splitting the atom for the very first time. A machine like that could have arrived in our solar system millions or even billions of years ago and settled into the one place nobody would ever think to look, among the millions of nameless rocks of the asteroid belt. And if that is true, then we should be able to ask a simple question. Have we ever actually seen one? The answer, maybe, is yes. And it has been sitting in plain sight in our catalogs for more than 170 years. Its name is 33 Polyhymnia. Polyhymnia is an asteroid in the main belt, the wide band of rocky debris that orbits the Sun between Mars and Jupiter, the leftover rubble from the building of the solar system. It was discovered on October 28, 1854, by a French astronomer named Jean Chacornac, and it was named after one of the 9 Greek muses, the muse of sacred song. For 170 years, it was nothing. Just one more entry in a list of hundreds of thousands of rocks, a faint point of light that crossed the telescope and went into the ledger and was forgotten. By every ordinary measure, Polyhymnia is boring. When astronomers break apart its light to read its composition, the technique we call spectroscopy, it comes back looking like a perfectly normal stony asteroid, the same broad family as the most common meteorites that fall to Earth. Same kind of rock you could pick up in a field. Nothing in its color, nothing in its orbit, nothing on its surface waves a flag. Everything strange about Polyhymnia comes from a single number, and that number is its density. Density is just how much stuff is packed into a given space. Lead feels heavy for its size because it is dense. Foam feels light because it is not. And every material has a density that is fixed by physics, by the kind of atoms it is made of and how tightly they pack together. This is one of the most reliable things we know. So when astronomers worked out the density of Polyhymnia, they got a result that should not be able to exist. In 2012, a survey compiled the masses of hundreds of asteroids, and for Polyhymnia, the figure that came out was staggering. Using a diameter of about 54 kilometers, which is a body roughly 33 miles across, a small mountain of a world, and a calculated mass that ran to an almost comically large number of metric tons, the density worked out to about 75 grams per cubic centimeter. Now let me tell you why that number should make the hair on your arms stand up. The densest stable element that exists naturally on Earth is osmium. You could hold a cube of it in your hand, and it would feel absurdly, impossibly heavy, like a trick. Osmium has a density of about 22.59 grams per cubic centimeter. Polyhymnia's number, 75, is more than 3 times denser than that. 3 times denser than the densest natural substance our planet has to offer. Let me make 75 grams per cubic centimeter into something you can actually picture, because the number is so far outside ordinary experience that it slides right off the mind. Take an ordinary soda can. Fill it not with soda, but with material at Polyhymnia's claimed density. And that one little can would weigh around 25 kilograms, roughly 55 pounds. A single soda can you could not lift with one hand. Fill a 1-liter water bottle with the stuff, and you would be trying to hoist 75 kilograms, the weight of a grown man, in a container you could hold in your palm. That is what 3 times denser than osmium actually means. It means matter packed so ferociously tight that a fistful of it outweighs a person. Nothing you have ever touched, nothing in any vault or laboratory or mine on this planet behaves that way. And yet, that was the number the measurement handed back for an ordinary-looking rock between Mars and Jupiter. And it gets worse, because Polyhymnia is not supposed to be made of osmium. It is supposed to be made of rock and metal, like every other asteroid. The densest thing a natural asteroid could possibly be, a solid core of nickel and iron with no empty space at all, tops out at around 7.8 to 8 grams per cubic centimeter. That is the ceiling that is as heavy as a rock in space is allowed to get. Polyhymnia's 2012 figure is not a little over that ceiling. It is roughly 10 times over it. It is as if you weighed an ordinary boulder, and the scale told you it weighed as much as a truck. There is no natural material, nothing on the periodic table, nothing we have ever pulled from the ground or watched fall from the sky that can be packed that tightly by nature. By the ordinary rules, an object like that simply cannot be a normal asteroid. And that is the anomaly that refuses to die. The question is what you do with a number that impossible, and the answer splits into 2 roads that could not lead to more different places. Before we follow the exciting road, we have to be honest about the boring one, because the boring one is probably correct. and you deserve to understand exactly why. So let me ask you a question that sounds simple and is not. How do you weigh an asteroid? You cannot put it on a scale. You cannot fly out to the asteroid belt with a bathroom scale and ask a 50-kilometer mountain to step on. So how do we actually know the mass of any of these rocks? The answer is gravity. Everything with mass pulls on everything else with mass. The Earth pulls on you, which is why you have weight. And an asteroid, even a small one, pulls ever so slightly on its neighbors. So when two asteroids pass near each other in their orbits, each one tugs on the other, just a little, and their paths bend by a tiny amount. If you measure that bending precisely enough, you can work backward and figure out how much mass it would take to cause it. That is how we weigh the unweighable. We watch how hard it pulls. Let me put that in terms you can feel. Imagine trying to figure out the weight of a single grain of sand by watching how it nudges another grain of sand as the two drift past each other in a swimming pool, except the swimming pool is millions of kilometers wide, and you are watching from the far side of it through a telescope, and the whole thing is happening over months. That is roughly the difficulty of weighing an asteroid by its gravity. Now add another twist. To turn that mass into a density, you also have to know the object's exact size, its volume, and the size of a distant asteroid is itself an estimate, pieced together from how much sunlight it reflects and how much heat it gives off. So you are dividing one uncertain number, the mass, by another uncertain number, the volume, and small errors in either one get magnified in the answer. When the inputs are shaky, the output can be wildly, spectacularly wrong, and nobody in the field pretends otherwise. Here is the catch, and it is an enormous catch. The gravity of a small asteroid is incredibly, almost laughably weak. The tug it gives its neighbor during a brief pass is faint to the point of being barely there, a whisper of a deflection that we are trying to read across millions of kilometers of space. And when you are trying to measure something that faint, the errors can be gigantic. A small mistake in tracking, a slightly wrong assumption about the neighbor's path, and your answer for the mass can be off by a factor of 2, or 3, or more. This is not a precise science. It is one of the hardest measurements in all of astronomy, and the people who do it will tell you so themselves. And this is the part that the thrilling version of the story tends to skip. The astronomer who produced that 2012 density figure flagged it personally as unrealistic. He did not announce that he had found a superdense alien object. He published it as an outlier, the kind of crazy result that small body gravity studies cough up when the signal is too weak and the error bars are too wide. And we know these outliers get corrected because it has happened before. There was another asteroid in the same dataset, a rock called 675 Ludmilla, that also came back with an impossible density. And when better data came in later, Ludmilla's number was quietly revised back down to something completely normal. The anomaly evaporated. It was never a strange object. It was just a hard measurement that got cleaned up. So that should be the end of it, and for most scientists, it is. But Polyhymnia did something Ludmilla did not. It held on. In 2023, a new analysis used more recent and more precise orbital data to take another swing at Polyhymnia's mass, and it got a lower number than the 2012 figure. The density dropped, but, and this is the hook the whole mystery hangs on, it did not drop to normal. With the more carefully measured size, the new density came out to about 12.4 grams per cubic centimeter. That is far below the absurd 75, but it is still about 50% denser than solid iron and nickel. It is still over the ceiling. The number got smaller, it got more careful, it got more defensible, and it was still too high. That stubbornness is what pulled in the physicists, because some of them asked a wild conditional question. If, hypothetically, the density really were that high, What could possibly be made of it? And the only answers anyone could offer involved matter beyond the edge of the known periodic table, hypothetical super-heavy elements clustered in a predicted zone called the island of stability, elements that may not even exist. The word if was carrying the entire weight of that idea, but the if would not go away. And that is the doorway through which the second road, the strange road, comes walking in. So let us walk down that strange road, all the way, without flinching, and see where it goes. Let us assume, just for the length of this investigation, that the anomaly is not an error. Let us assume the number is trying to tell us something true. What would it mean? It would mean that 33 Polyhymnia is an object that looks exactly like a stony asteroid on the outside. Ordinary rock, ordinary color, ordinary orbit, while concealing something on the inside with the gravitational pull of a material that nature is not allowed to make. And if you have been following along, you already know what kind of thing was designed to do precisely that. A machine built to hide. A machine that wears local rock as a costume and conceals its true nature underneath. A von Neumann probe. Polyhymnia, in this reading, is not a rock at all. It is a parked machine, sitting in the asteroid belt wearing a 54-kilometer shell of harvested stone, and the density anomaly is the one detail the disguise could not quite hide. The mass of whatever is inside, bleeding through into the gravity, where a careful enough measurement could catch it. And now, consider the scale of the thing, because this is where it stops being abstract. People talk a lot about interstellar visitors, those rare objects that fall into our solar system from another star. The channel has looked closely before at 3I/Atlas, the interstellar object that came barreling through and set off so much argument about whether it was natural or something else. 3I/Atlas is a serious object, and Polyhymnia, by volume, is on the order of 1,000 times larger than it. 1,000 times the room inside. This is not a drone. This is not a scout. A body this size is large enough to conceal an entire factory, an industrial complex, a replication facility, a mothership, anything you care to imagine, with kilometers of rock to spare as camouflage over the top. If you wanted to hide a base in our solar system and never be found, you could hardly design a better container than a giant, boring, cataloged asteroid that everyone has already decided is nothing. But what, physically, could give an object a rocky shell and the gravity of something impossibly dense? The speculation here gets exotic fast, and I want to walk you through the leading possibilities, because they are genuinely fascinating, even though, as you will see in a moment, every single one of them runs into a wall. The first idea is the most dramatic: a contained micro black hole at the core, a tiny artificial singularity with an event horizon measured in billionths of a meter, sitting at the center of the asteroid like a seed. A black hole is the densest thing the universe permits. Mass crushed down toward a point, and a small amount of it would read, from the outside, as an object far heavier than its size should allow. It would also be a power source beyond anything we can build, feeding the machine energy without any need for fuel tanks. The second idea is stabilized exotic matter, a core of something like neutronium, the crushed material of a neutron star, or strange quark matter held together by force fields we do not have, a few grams of the densest stuff in the cosmos kept stable far from the dying star that should be required to make it. The third idea is active gravitational engineering, the asteroid carrying a device that bends space-time itself, manufacturing extra gravity without extra mass, the same kind of technology that, in theory, could let it quietly nudge its own orbit or hide its own heat. And the fourth is the eeriest of all, that the asteroid is mostly a thin shell wrapped around a computer, a quantum computational core running at densities approaching the physical limits of computation, and the gravity we measure is the sheer energy of that titanic machine thinking, made heavy. A disguised mind, sitting in the dark, processing. And think about how good the hiding place actually is, because the asteroid belt is not the crowded boulder field the movies show you. It is enormous and nearly empty, a sparse scattering of rocks separated by hundreds of thousands or millions of kilometers of nothing. And there are millions of bodies in it, large enough to matter, the overwhelming majority of which we have never visited, never photographed up close, and never weighed by anything more than that faint gravitational whisper. We have laid eyes, really laid eyes, on a handful. The rest are points of light and entries in a ledger. If you wanted to disappear inside our own solar system, you would not hide on a planet where we are watching closely. You would become one more anonymous rock in a population so large we will not finish properly cataloging it this century. You would pick an orbit, paint yourself the color of your neighbors, and switch off. And the longer you stayed quiet, the more thoroughly the watchers below would file you away as nothing, until your own dismissal in their records became the strongest lock on the door. Any one of those, if it were real, would let a dormant probe lie in the asteroid belt for ages, drawing on local resources, replicating in silence, lighting up only when something down on the third planet caught its attention, and the believer's argument closes with a line that is genuinely hard to shake. We dismiss Polyhymnia, they say, precisely because its density is impossible for a natural asteroid. But impossible for a natural asteroid is exactly the signature a disguised machine would leave. Our own scientific caution, our reflex to throw out anything that looks too strange, becomes the final, perfect layer of the camouflage. The better the disguise, the faster we dismiss it. It is a beautiful argument. It is also, as we are about to see, where the whole story quietly breaks in half. I want to be the honest guide here, not the salesman, because the difference between those two things is the entire reason this channel exists. So let us take everything we just built and hold it up against the cold light of the physics, one piece at a time, and watch what survives. The short version is not much. The long version is more interesting than the short version, so stay with me. Start with the density itself, the foundation the whole tower is built on. We already walked through how asteroid masses are measured by reading the faint gravitational tug of a tiny body across millions of kilometers, and how that measurement is one of the most error-prone things in astronomy. We already saw that the astronomer who first published the 75 figure called it unrealistic himself. And we already saw the precedent, 675 Ludmilla. Another impossible density in the very same data set that simply melted away when better numbers arrived. The most likely explanation for Polyhymnia's anomaly is not exotic matter. It is not a black hole. It is the same boring gremlin that haunts every small body measurement, a faint signal, a long chain of assumptions, and an error bar wide enough to drive a truck through. The number is probably wrong, in the same way Ludmilla's was wrong. And the only reason it has not been fully cleaned up yet is that nobody has flown out there to nail it down. Then there is the meteorite problem, and this one is quietly devastating. About 98.5% of all the meteorites that fall to Earth are broken pieces of asteroids. They are literal samples of the asteroid belt, delivered to our doorstep for free, and we have collected them by the tens of thousands. We have weighed them, sliced them, analyzed their every atom, and not a single one of them, not one, is made of anything denser than nickel and iron. If the asteroid belt contained even one genuinely ultra-dense object, you would expect its fragments, its chips, and shards from billions of years of collisions to show up somewhere in that enormous collection. They never have. The sky has been mailing us pieces of the asteroid belt for all of human history, and every piece obeys the ordinary rules. On top of that, when we read Polyhymnia's own light directly, the spectroscopy, it looks like plain, stony material. There is no exotic glint, no strange signature, no hint of anything beyond ordinary rock. The outside looks normal because, in all probability, the outside is all there is. Now turn to those 4 beautiful exotic cores, because they are where the romance really comes apart. The micro black hole. Here is the thing nobody mentions in the thrilling version. A black hole small enough to fit inside an asteroid would not sit there as a calm little power source. Tiny black holes are not stable and quiet. They radiate, a process predicted by Stephen Hawking, and the smaller they are, the more furiously they blaze. A black hole that's small would evaporate in a searing flash of energy, not lie dormant for 1 billion years. It would be less like a battery and more like a bomb with a very short fuse. The exotic matter idea fails for a related reason. Neutronium and strange quark matter, as far as we understand them, are only held together by the crushing gravity of a neutron star, an object more massive than our sun squeezed into the size of a city. Pull a spoonful of that material out into ordinary space, and it does not stay a dense little marble. It comes apart violently. And the gravitational engineering and the warp bubble ideas all run into the same brick wall, which is that they require negative energy, a kind of exotic ingredient that no one has ever produced, in quantities no one knows how to reach, using physics that currently exists only on chalkboards. These are not engineering options sitting just over the horizon. They are names we have given to things we cannot do and may never be able to do. There's also a simpler principle quietly working against the whole exotic picture, one that scientists lean on constantly, and it is worth saying out loud. When you are faced with 2 explanations for the same observation, and one of them requires nothing but known, ordinary, boring physics, while the other requires inventing brand new physics that has never been seen, the ordinary explanation wins until the evidence forces your hand. It is not a law of nature, just a rule of thumb, but it is a rule of thumb that has paid off 10,000 times in the history of science. And here the 2 explanations could not be more lopsided. On one side, a hard measurement came out wrong, the way hard measurements often do, exactly the way the same kind of measurement already came out wrong for a neighboring asteroid that got corrected. On the other side, an asteroid contains a stable artificial black hole, or a marble of neutron star matter sitting impossibly calm in open space, or a space-time bending engine, all of it built by a civilization we have no other evidence has ever existed. One of those explanations asks you to believe that astronomers sometimes make measurement errors. The other asks you to rewrite physics and populate the galaxy with ghosts. They are not close, and that leaves the cleverest part of the believer's case, the part that felt unbeatable. The idea that our dismissal of Polyhymnia is itself the proof, that the perfect disguise is the one that makes scientists look away. I want to take that seriously, because it is seductive, and then I want to show you why it is a trap. The problem is that it is unfalsifiable. Think about what that argument actually does. If we measure the asteroid and find nothing strange, the believer says, of course, that is what a perfect disguise would show. If we find something strange, they say, see, I told you. There is no possible observation, no measurement, no result that could ever prove the believer wrong, because every outcome gets folded back in as confirmation. And a claim that can absorb any evidence, that can never be tested, never be wrong, is not science. It is a story that has sealed itself off from reality. It can be thrilling, and it can still be empty, and those 2 things are not in conflict. The same logic that makes Polyhymnia a probe would let you point at any rock in the sky and call it a spaceship, and dare anyone to prove otherwise. That is not a discovery. That is a door that only opens inward. So the strange road, followed all the way to its end, runs into a wall built of meteorites and Hawking radiation and the basic rules of what science is allowed to be. The anomaly is almost certainly a misweighed rock. And yet, I am not quite ready to walk away. And in a moment, I will tell you why. Because there is one more voice in this argument worth hearing, and it belongs to someone who spent his career insisting that the right answer to a strange object is not to dismiss it and not to worship it, but to go and measure it. There is a reason the comparison to 3 I/Atlas keeps coming up, and it is not just about size. When that interstellar object passed through our solar system, most of the scientific world treated it as an ordinary, if rare, chunk of cosmic ice and rock, and moved on. But a smaller group of serious scientists argued for something different. Not that it was definitely alien, but that we should take the possibility seriously enough to actually look, to point our best instruments at it, and test the strange explanation, instead of waving it away on reflex. That posture, the refusal to dismiss an anomaly simply because the mundane answer is more comfortable, is worth borrowing here, because it is the only honest way through a story like Polyhymnia's. The temptation, when you hear the words alien probe, is to roll your eyes and stop thinking. And most of the time, that reflex serves you well, because most extraordinary claims really are nonsense. But the same reflex, taken too far, becomes its own kind of failure. If you have decided in advance that nothing in the sky could ever be artificial, then you will explain away any anomaly, no matter how genuine, because your conclusion is already locked. And that is just the believer's unfalsifiable trap. Flipped upside down, the believer can never be proven wrong, because every result confirms them. The hardened skeptic can never be surprised, because every result gets normalized. Both of them have stopped doing science. Both of them have stopped looking. History is not kind to the reflex of automatic dismissal, and that is worth sitting with for a moment. For a long time, respectable scientists laughed at the idea that rocks could fall from the sky, because everyone knew there were no rocks up there to fall, and the peasants reporting stones dropping from the heavens were simply confused. The stones were meteorites, of course, real samples of the very asteroid belt we have been talking about, and the laughter was the error. The same pattern has repeated again and again. The thing that sounds absurd is usually absurd, but not always. And the entire job of science is to tell the difference by testing, not by deciding in advance which answers are permitted. That does not mean every wild claim deserves a spacecraft. It means that when a wild claim attaches itself to a genuine, stubborn, unexplained anomaly, the grown-up response is not a smirk. It is an instrument, and Polyhymnia is exactly that awkward combination. The claim attached to it, that it is an alien machine, is almost certainly wrong, but the anomaly underneath the claim, the density that will not behave, is real, published, and unresolved. You are allowed to hold both of those thoughts at once. In fact, holding both at once is the only intellectually honest place to stand. The mistake is collapsing the two into one, either deciding the wild claim must be true because the anomaly is real, or deciding the anomaly must be nothing because the wild claim is silly. Those are both lazy. The anomaly earns a measurement on its own merits, regardless of the story someone has draped over it. The honest position lives in the narrow space between those two, and it is the position this whole channel tries to hold. Take the wonder seriously. Take the physics more seriously. And when you find an anomaly that you genuinely cannot explain, an asteroid whose density refuses to come down no matter how carefully you measure it, do not fall in love with it and do not throw it away. Do the one thing that actually settles arguments. Go and look. And the remarkable thing about Polyhymnia, the thing that makes it more than just a campfire story, is that going and looking would be almost embarrassingly easy. Here is what almost nobody tells you about this mystery. We could end it, not in some far future of warp drives and starships, but with technology we have, right now, today, sitting in clean rooms and on launch pads. Polyhymnia is not in another galaxy. It is in our own asteroid belt, between Mars and Jupiter, a place we have already sent spacecraft to more than once. It is not going anywhere. It has been holding still for 170 years of human observation, and it will hold still for 170 more. A modest robotic mission, the kind of thing that costs a fraction of what we spend on far less interesting questions, could fly out to Polyhymnia and settle the entire debate in a single afternoon of data collection. You would carry 3 instruments, and only 3. A gravimeter to measure the object's gravity field directly, up close, with none of the crippling uncertainty that comes from reading a faint tug across millions of kilometers. That alone would tell you, definitively, what this thing actually weighs, and how that mass is arranged inside it. A mass spectrometer to sample the composition and find out whether the surface is the ordinary stone the spectroscopy suggests, or something stranger underneath. And a high-resolution imager, a good camera to simply look to see whether the surface is the cratered, dusty, unmistakably natural face of a rock, or whether there is structure under the regolith, geometry, anything that nature does not build. Check for heat it should not be giving off. Check for emissions it should not be making. 1 flyby, 3 instruments, a few hours of data, and a question that has lingered for over a decade would be answered for good, one way or the other. And we have done exactly this kind of thing before, which is what makes the inaction so telling. We have flown spacecraft out to specific asteroids, orbited them, even landed on them and scooped up samples and flown them home. The capability is not theoretical. We have a working playbook for visiting a rock in the belt and interrogating it from up close. We have pointed it at asteroids chosen because they were convenient, or because they made good practice targets, or because they posed a faint impact risk worth studying. We have simply never pointed it at the one asteroid in the entire catalog whose measured density openly violates the rules of matter. Of all the rocks we could choose to go weigh in person, the single most anomalous one, the one object that a curious species might think to check first, is the one we have collectively decided is not worth the trip. That choice is not about technology or money. It is about expectation. We do not go because we already know what we would find. We have the technology. What we lack is the will, and the reason we lack the will is itself revealing. We do not send that mission because we already know, or believe we know, that there is nothing there. The density is an error. The case is closed, and 999 times out of 1,000, that confidence is completely justified. But the entire unsettling point of this story is the 1,000th case. The one where the thing we were too sure about to bother checking turns out to have been the most important object in the sky. The anomaly that refused to die is cheap to kill. We simply have not bothered to load the gun. And that brings us back, in the end, to the deepest and most uncomfortable question this whole story was really about. So let me bring it all the way home, and let me be completely straight with you about where the evidence actually lands, because you have earned that after coming this far. 33 Polyhymnia is almost certainly a rock, not a machine, not a mothership, not a sleeping intelligence wearing a costume of stone. A misweighed rock, its impossible density, the ghost of a measurement we are not yet able to make cleanly, destined to be quietly corrected someday, the way 675 Ludmilla was corrected, sliding back down into the ordinary where it has always belonged. The meteorites say so. The spectroscopy says so. The physics of black holes and exotic matter says so. If you want me to bet, I bet on the rock. Every time. And the timeline argument that opened all of this, the saucers that arrived 6 years too early, the bomb that supposedly rang the dinner bell. It has its own quiet holes once you stop and press on it. It assumes the sightings of 1947 were genuinely something unexplained, when most of them have long, dull explanations. weather balloons, and misjudged aircraft, and the heavy secrecy of a country in the opening years of the Cold War. It assumes the trigger had to be Hiroshima, when our radio noise had already been leaking into space for years before the bomb. And it assumes, underneath everything, that something responded to us at all, which is the very thing it is supposed to be proving. The elegant logic of already here only holds if you grant all of that for free, and you should never grant anything for free. But here is what I cannot quite shake, and I do not think you will be able to either. The reason we are so quick to dismiss Polyhymnia is that an object like that is impossible by the rules of nature, and that exact reflex, that fast and confident wave of the hand, is precisely the cloak that a thing built to hide would want us to wear. I am not telling you Polyhymnia is a machine. The evidence says it is not. I am telling you something stranger and harder to put down, which is that if a machine ever did want to hide in our solar system, disguising itself as an ordinary asteroid would be very close to perfect, and our own certainty that there is nothing to see would be the last and best layer of its disguise. The camouflage does not just hide the object, it hides our willingness to look. There is a particular kind of humility this story asks of us, and it has nothing to do with believing in aliens. It is the humility of admitting how thin our actual knowledge of our own neighborhood really is. We have walked on one other world and sent robots to a scattered few. We have cataloged a great many objects as points of light and orbital numbers, and called it knowing them, when in truth we have never seen most of their faces. Knowing that a rock exists and knowing what a rock is are not the same thing, and the gap between those two kinds of knowing is where every interesting possibility lives. Our solar system holds millions of rocks we have never visited, most of them never named, never imaged, never weighed by anything but the faintest tug of their gravity. We have cataloged a fraction. We have visited a handful, and we tell ourselves with great confidence that we would know, that we would notice, that nothing could be hiding out there among the rubble without us recognizing it for what it is. Polyhymnia is the small, stubborn crack in that confidence. It is almost certainly nothing, but it forces the question that the whole journey was really about, the one that outlives the asteroid itself. In a sky full of objects we have decided are not worth a second look, how sure can we honestly be that we would recognize the one that was looking back? The anomaly that refuses to die is probably just bad data. The unease it leaves behind is something else entirely, and it does not correct itself with better measurements. It only grows the longer you stare at the dark and wonder what, in all that silence, might be staring back. We have the instruments to find out. The only thing we have never had is the nerve to point them and admit we might be wrong.